Hi everyone, welcome back to PRAKASAM tutorials. In this video, I am going to discuss about movement generating function and characteristic function of a Poisson random variable. First, we are going to discuss about movement generating function of a Poisson random variable. So the random variable capital X is a Poisson random variable. Then the movement generating function is given by mx of t is equal expectation of e power tx, which is equal x is equal to sigma x is equal to 0 to infinity e power tx into p of x. So where p of x is the uh, Poisson distribution of a random variable, that expression is e power minus lambda into lambda power x by x factorial. Substitute that expression into that equation into RHS term of this equation. We get movement generating function mx of t is equal sigma x is equal to 0 to infinity e power tx into e power minus lambda into lambda power x by x factorial. So e power tx into e power tx into lambda power x is written as lambda into e power t whole to the power of x. So RHS term is written as e power minus lambda into sigma x is equal to 0 to infinity lambda power x into e power tx is arranged as lambda into e power t whole to the power of x by x factorial. So now substitute different values of x, we get first substitute x is equal to 0 e power minus lambda into substitute x is equal to 0 lambda e power t whole to the power of 0. So lambda e power t whole to the power of 0 is 1 by x factorial is 1. First term is 1. Next substitute x is equal to 1. The second term is lambda e power t whole to the power of 1 by 1 factorial plus next substitute x is equal to 2. The third term is lambda e power t whole square by 2 factorial plus and so on. So substitute different values of x, we get this within the bracket term. So this within the bracket term is the expansion of e power x. So what is the expansion of e power x? E power x is 1 plus x by 1 factorial plus x square by 2 factorial plus and so on. So using this expansion, this within the bracket term is e power lambda e power t. So e power minus lambda into e power lambda e power t is written as so e power lambda t minus lambda. E power lambda t minus lambda, for both the terms lambda is the common. C power lambda into e power t minus 1. So this is the expression of movement generating function of a Poisson random variable. Next we are going to discuss about characteristic function of a Poisson random variable. The random variable capital X is a Poisson random variable. Then the characteristic function of the Poisson random variable is given by pi x of omega is equal expectation of e power j omega x. Now where x is varies from 0 to infinity, that is sigma x is equal to 0 to infinity e power j omega x into p of x. So this is the expression of characteristic function of a random variable for discrete case. But Poisson distribution expression is p of x is e power minus lambda into lambda power x by x factorial, and substitute Poisson distribution expression here, we get sigma x is equal to 0 to infinity e power j omega x into e power minus lambda into lambda power x by x factorial. So lambda power x into e power j omega x is written as lambda into e power j omega whole to the power of x. So therefore the RHS term is e power minus lambda into sigma x is equal to 0 to infinity lambda into e power j omega whole to the power of x by x factorial. So in this term, substitute different values of x, we get this within the bracket term. First substitute x is equal to 0, lambda e power j omega whole to the power of 0 is 1 by x 0 factorial is 1. First term is 1. And second term, substitute x is equal to 1, we get this second term. Substitute x is equal to 2, we get this third term. So this is the within the bracket term. Substitute different values of x in this summation. So this within the bracket term is the expansion of e power x, that is e power lambda e power j omega. So therefore pi x of omega is equal e power minus lambda into e power lambda e power j omega. So e power lambda e power j omega minus lambda, that is written as e power lambda into e power j omega minus 1. So this is the expression of characteristic function of a Poisson random variable. So this expression we can also derive from the moment generating function of the Poisson random variable. So this is the expression of moment generating function of the Poisson random variable. In this final expression, small t is replaced by j omega. We get the expression of characteristic function of the Poisson random variable. Substitute small t is equal to j omega. We have e power lambda into e power j omega minus 1. So that is the alternative derivation of the characteristic function of a Poisson random variable from the moment generating function of the random variable. So this is the derivation, or this is the concept of moment generating function of a Poisson random variable and characteristic function of a Poisson random variable.